Unit Operation Classroom. Today we are going to discuss tanks in series model, how to estimate the conversion in a real reactor using the tanks in series model. First, we'll read the problem statement. My name is Shekhar Bhattacharjee. A first-order homogeneous liquid phase reaction A to B occurs in a non-ideal isothermal reactor operating at steady state. So let's assume this is my reactor. This is non-ideal. So this is not a perfect ideal CSTR. This is not an ideal flux flow reactor. This is a non-ideal reactor. Some amount of non-ideality is involved. We'll see what is meant by non-ideality or what causes non-ideality. The variance of residence time distribution RTD from a pulse tracer experiment is 4 minutes squared. We will see what is a pulse tracer experiment and how to estimate the variance from the RTD, residence time distribution data. Volumetric flow rate of the feed is 5 liters per minute, and the volume of the reactor is 25 liters, and the reaction rate constant is given. So basically here the feed, which is a liquid reactant A, is coming in. The flow rate is given 5 liters per minute, and there is a first order reaction is taking place inside the reactor. The first order rate constant is given. Volume of the reactor is 25 milliliter, and of course a product, that means unreacted reactant, and the product B comes out from here. This is steady state homogeneous liquid phase reaction. So this is a non-ideal. So this is an actual reactor. So and value of course variance is given here, and we'll see what it means. So we have to use the tanks in series model. Based on the tanks in series model, that we have to estimate the conversion. So basically what we're going to use, so I would say, read this tanks in series model from any standard textbook, let's say Levenspring or Fogler. But basically, since this is not a single CSTR, this is not single PSTR, this is an actual non-ideal reactor, we'll assume this to be a series of CSTRs. But how many? So we have to find out that how many series of CSTS in series actually represents this particular non-ideal reactor. How to do that and how to do the calculation, we'll see. So this is the tanks in series model. So we assume there are n number of CSTS in series, and the standard deviation is given. So we have to find out. First, we'll find out how many tanks in series will represent this non-ideal reactor, the actual reactor, and what will be the conversion then. So first, this one will determine the hydrodynamics inside the reactor. That means whatever the reactants coming in, we had it been a CSTR, that would be a complete mixing, but or the PFA, there is no mixing at all, just goes out as it is. But there is some imperfect mixing here, so there's some short circuiting, etc., etc. But we'll assume, we'll take a model here which has several CSTs in series, and we'll find out how many reactors N will represent this non-ideal reactor. First of all, these are all very standard equations. Look in the Levenspiel or Fogler, these are given already for tanks in series model. This one here, the standard deviation, this is the variance. Standard deviation is sigma t. Variance is given by tau squared divided by n, where tau is the mean residence time. So we can calculate the tau very easily because the volume of the reactor is given, flow rate is given. So the average residence time is 5 minutes. So basically here, although there is a lot of non-ideality presence, that means all the fluid elements do not spend exact the same amount of time inside the reactor. But overall, the average residence time of the fluid is 5 minutes. So this value is already known to you, which can be calculated like this. And this value is given. We'll see how this value is estimated from actual reactor experimental data. So from here, we can find out the value of N. And the value of N comes to be 6.25. So what it really means that for the actual reactor here, if we have 6.25 reactors, Now, when we say 6.25, so we don't make it 7. We don't make it 7. No, we keep 6.25 because n is just a parameter here. So we assume that if there is 6.25 station series, that hydrodynamics actually represents this non-ideality of this particular reactor here. So there are two parts. One is the hydrodynamics part, and the second, of course, is the then calculating the conversion. Okay. Just yes, so this n is 6.25. We say we do not round off and make an integer since n is a parameter of the model. So we don't make it 7. So we don't make it 7. We keep this n is 6.25 as it is. It is just a parameter. Uh, just on a side note, to estimate the peak here, so if there is a ET curve here, so if we just see this one, if there's so as you can see, there'll be there'll be a peak here. So the peak comes here. It's in 4.2 minutes. So that is the equation to calculate the peak, and this is the average residence time. What's the average residence time here? So basically, if we take a single stage here, then if we take the total volume divided by total, so that is the 5 minutes. Okay, so we'll graphically represent this average residence time and the peak in the next figure here. So this is my, let's say, the pulse stress experiment. This is a tank in series model. So what it basically says, so let's say here, this is my reactor here, and this is the actual non-ideal reactor. And so there is a carrier fluid here, so let's say this A, and we inject a tracer here. So inject a tracer, which is non-reacting with A, which is non-reacting, so there should not be any reaction. So we just inject in one push here. So that is like a Dirac delta function. Just it goes like this. Let's say we schematically we show this like, but actually this is a Dirac delta function, 0 times. We push here, and what happens? So some fluid, so it just comes and gets mixed with here. Some fluids just come out, come out immediately. Some stays a very long time. So basically, what you see here, some comes out immediately, and some starts coming out, and it reaches a peak concentration of this tracer here, which we have injected here. So we measure the concentration here. So the peak concentration happens around 4.2 mils, which we have calculated right here. So this is the peak concentration. And the average residence time, which is calculated right here. So this basically right here. So this is my average residence time here. And so this is 5 minutes. This average residence time. Peak is 4.2 minutes. This is kind of like skewed basically because it just goes like this. And the variance, of course, is 4 minutes squared. So around the average, if we can take plus minus 1 sigma, so that would be a band right here. So just read these things in a standard textbook. So this is my RTD output here. And this is the ET curve. We'll see how this ET curve is constructed from actual experimental data. Since we have determined the hydrodynamics and we say the actual reactor may be represented by 6.25 CSTS in series. So, and that's the over residence time. So now we can calculate the conversion in a series of CSTS, 6.25 CSTS. So for n tanks in equal volume, residence time of this tau over n. So you can calculate the value of CA over C0. This is my CA0, and this is the concentration which is coming out. So as you can see, this is 0.176. So outlet concentration from this 6.25 CSTS in series, assuming this is to represent the hydrodynamically the actual reactor here. So this CA over C0, that means this exit concentration is just 17.6% of the outlet concentration here. And from there, of course, we can easily calculate the conversion, which is 82.4%. All the details are shown in this website. Now let us interpret the answers. First of all, for the non-ideal reactor of our problem, we just said we have seen n is equal to 6.25. That means the actual reactor can be represented hydrodynamically as 6.25 in series, and the conversion, if we do the conversion in this one here, so that should be 82.4%. Therefore the actual in the actual reactor, this should be the conversion, assuming that the tanks in series model applies to this non-ideal reactor. Now, let us compare this one. Had we just done the same thing, that same CH0 and the flow rate coming in and it is coming out from a single CSTR. Okay, single reactor. So CSTR, a back mixed reactor. In that case, this is a very standard equation. It's just 66.7% in the conversion here. Okay. Um, had it been just a block flow reactor, assuming the same flow rate and therefore the same residence time, and as you can see that the conversion the block flow rate to 86.5%, we all know that the conversion at block flow reactor for the same parameters would be higher than that in a back mix reactor. So if we can summarize here, the conversion in the so if you conversion single CST would have been 66.7%. Conversion in a plug flow reactor with the same parameters here, same parameters would have been 86.5%. Here, of course, n is equal to one single CST, and we know plug flow reactor is represented as an infinite CSTS in series. So that's n tends to infinity. You'd see any textbook. So in a single CH2 would have been n is equal to 1. The conversion would have been 66.7%. In a plug flow reactor, which of course can be represented as n tending to infinity, the conversion would have been 86.5%. But in our non-ideal reactor of the problem, we have determined that n is equal to 6.25. That means 6.25 CH2 in series, and the conversion is 82.4%. So this is somewhere in between and here, and this of course conversion is in between these two. So this is an ideal CSTR, this is an ideal plug flow reactor, and this is intermediate. Somewhere we can just say this is closer to this number, is kind of like on the larger side. So we say this is constantly closer to a plug flow reactor. Okay. Let's look at the RTD of ideal CSTR and PA first. For an ideal CSTR, so this is a variance, and this, of course, the standard deviation is 5 minutes. So the variance should be equal to tau squared. So since tau is 5 minutes, an ideal CSTR has no dead pockets. So if we assume an ideal CSTR, so what happens anytime the feed comes in, it gets immediately back mixed, properly mixed, immediately mixed with air. So there are no dead pockets like the dead pockets, etc., which come out much larger. There is no dead pocket for an ideal CSTR. Its broad RTD results from perfect instantaneous mixing and lambda withdrawal from the product. So it has a broad RTD. So basically, this is kind of like broad, and this frequency standard deviation is approximately this tau square, which is 25 minutes. Okay. For an ideal CSTR. Okay. For an ideal plug flow reactor, this is equal to 0. All fluid elements spend exactly the same time inside the reactor. So for an ideal plug flow reactor, why this standard deviation is here, let's say if a bunch of fluid element comes in and it gets pushed by the next batch and in the whole thing and moves all the fluid elements move together, and finally all the fluid elements come out as just in spending exactly the same amount of time. So there's no variation. There is no variation in the amount of time spent by each element, assuming there is of course no radial backmixing and actual backmixing here. So therefore, this standard deviation is equal to 0, and the variance of course also comes out to be equal to 0. So that's from ideal plug flow reactor. For our unideal reactor, this is 2 minutes. So for an ideal CSTR, this would have been equal to tau squared. This is equal to 5 minutes. For an ideal plug flow reactor, standard deviation is 0 minute, and for a non-ideal reactor of our problems 4 minutes, since significant tau squared is given as 4 minutes squared in the problem. So this is equal to 2 minutes. Okay. What is the interpretation of the variance? RTD variance tells us how widely the residence time of fluid elements are spread around the mean residence time. So if my ET curve here, so basically it just goes like this. So how widely this is just spread in the ET curve, that's what is given by the variance. For it could have been something like this. right? In this case, the variance is much lower. So this is a much sharper peak. If it is something like this, of course, the variance is much larger. So here, basically, this would be like for a CS tier, and for the narrower, that would be of a plug flow reactor. So large variance means greater mixing, back mixing, channeling, and stagnant fluid elements inside the actual reactor. So for, as I said, for a CS tier, the standard deviation is 5 minutes. For n is equal to 1, ideal CS tier. For plug flow reactor, standard deviation would be equal to 0. There is no spread because all of them spend exactly the same amount of time. All the fluid elements which is coming in goes out at the same time after spending exactly the same amount of residence time in the plug flow reactor. And we know a plug flow reactor can be expressed as n tan into infinity number of CSTs in series. For us, the Z is 6.25 and the standard deviation is 2 minutes. So non-ideal reactor is considerably closer to plug flow reactor. Okay, this one. Okay. Real reactor, and so what does it mean? This means that the reactor vessel has much lower variance, meaning narrower RTD than an ideal CST. As I said, for an ideal CST, it is something like this, whereas if it is something like this, for a plug flow, for our reactor, it is much narrower. Okay, so it's associated. The flow pattern in the reactor is more like plug flow than CST. The actual reactor is hydrodynamically represented by an effective tanks in series parameter N is equal to 6.25, indicating considerably less overall back mixing, which is in CST, characteristic of CST, than an ideal CST. Okay. What could be a possible reactor configuration? This is just a guess. This is just a guess. So do not assume that this is the correct one. Just schematically, this is a guess. Let's say if it is something like this, and this is compartmentalized in, let's say, 6.25, assuming 6.25, assuming. So in each one, there's a local recirculation and mixing within each cell, and there's a continuous flow of actual flow of the fluid like this. Okay, so and this could be like n is 6.25 cells here. So these are like baffles, allows flows to the next cell, and here the reactant comes in, and here the product goes out. This would be a typical schematic diagram of a possible schematic representation, hypothetical reactor configuration. What could be an example of such a thing? Continuous acid catalyzed hydrolysis of an ester, let's say ethyl acid. So this is my ethyl acetate, and this is my water. When this gets hydrolyzed, we get acetic acid plus ethanol, right? With large water presence, this becomes a pseudo first order reaction based on the proportion to the concentration of ethyl acid. So this could be an example of the representation of our problem. Baffled tubular compartmentalized reactor with moderate axial mixing, which we have seen here, compartmentalized. Okay. The variance is lower than an ideal CST and closer to a plug flow. The overall residence time is 5 minutes, but effective in each stage would be 0.8 minutes divided by 6.25. So in each stage, there will be 6.24 minutes, but there's an axial flow. It keeps on going like this. The overall residence times for fluid elements are less widely dispersed around the mean than in an ideal CST, indicating lower overall back mixing and more plug flow behavior, which we have already seen. Let's look at the RTD comparison of CST and non-ideal reactor. So this is already what we have seen. This is my ET curve here. Okay, and this is the actual reactor, and it's equal to 6.25 we have seen. Had it been a plug flow reactor, as we said, if it's a plug flow reactor, the ET curve, so all the fluid comes in and just moves as a en bloc together, and it comes out after spending the residence time of 5 minutes, all the fluid elements. Okay, there's no distribution of the residence time of the fluid elements. So basically here the concentration will be 0, and it comes again as a Dirac delta function, something like this in the Dirac delta function. So for an ideal plug flow reactor, all fluid exit at time t is equal to 5 minutes. This is right here, which is the average residence time. So, and of course, the standard deviation is 0 minute. This spike is enhanced for visual clarity. It's not like this. Okay. For an ideal CS chair, the ET curve would have been just follow this equation. Just see any standard textbook. This is basically given by this equation right here. See any standard textbook, Fogler or Lemonspiel, and the ET curve would show. I have shown all the details here in this website. So it starts right here at 0 minute, and then it's an exponential decay curve. So goes something like this. Okay. So right from the initially, there's the highest concentration here. If it is a ideal CS tier. So for an ideal solicitor, it comes to the highest concentration, and there is an exponential decay like this. For a plug flow reactor, there is initially zero concentration, and then it comes out just together as a spike, again as a Dirac delta function, after spending the average residence time of 5 minutes. For the actual reactor, which is n is equal to 6 point non-ideal reactor, which we have characterized as n is equal to 6.25. So initially the concentration will rise and just go to a peak, which is 4.2 minutes, we have calculated. And this is my average resistance time. This is little skewed and it just goes like this. Okay, not like this. If something goes like this, doesn't goes like this. Okay. Um, this is at 5 minutes. Okay. Uh, all three RTDs have same mean residence time, 5 minutes. That means whether this is a ideal plug flow reactor, whether it's a single CS chair, or this is a non-ideal reactor. For all of them, the residence time, the average residence time, of course, is going to be 5 minutes for all three of them. Okay, so an ideal CS chair, n is equal to 1, single CS chair, average residence time is 5 minutes. Of course, standard deviation is 5 minutes, and the variance is 25 minutes squared. For a non-ideal reactor for problem, n is 6.25, average residence time again the same, 5 minutes, but standard deviation is 2 minutes, which you have calculated. It's given, not calculated, given, because the variance is given as 4 minutes squared in our problem. So this is already given. So this is my standard deviation. For an ideal plug flow reactor, which we know is n infinite number of CS chairs in series, the average residence time remains the same for all three of them. But of course, the standard variance is going to be equal to 0 minute because all the fluid elements exactly the same amount of time in the reactor. For an ideal reactor, we know this is the equation for the ET curve, and which it translated for this one. This is 5. So this is my equation for the non-ideal reactor. And for an ideal plug flow reactor, of course, this is given by this equation. This is the delta function. If we integrate the E curve, and that would be equal to 1, which you all know. ET of course is going to be always equal to 0 except 0 except when t is equal to 5. Otherwise, this is going to be equal to always equal to 0, which we know it is that would be always 0. Will be always 0 because whether this side or this side is set at this particular point, which is again a spike or Dirac delta function. How the standard deviation, the variance is measured. So how experimentally, this slide now shows you how experimentally we can calculate the standard deviation from an actual reactor. Okay, the data which have been given here, how that was calculated. What we do, let's say this is my actual reactor. We inject a tracer, which of course is going to be non-reactive. There should not be any reaction because we are determining the hydrodynamics inside the reactor. So inject a non-reactive tracer pulse at t is equal to 0. Again, a Dirac delta function. Measure pressure concentration CT at regular. So at this point, you continuously measure what's the concentration. You can use the spectrophotometer, maybe visible spectrophotometer, or maybe use a conductivity meter, etc., just to measure the pressure concentration. Okay, and we know this is the equation. Exit edge distribution is given like this, and this integrated over 0 to infinity equal to 1. Standard, see any standard textbook. The mean residence time is given by this equation here, which is this one right here, which of course experimentally is the volume of the reactor divided by the flow rate, which is going to be the same for whatever type of reactor you're going to choose, whether ideal CSJ, ideal plug flow reactor, or if it's a number of CSJs in series, the tanks in series model. RTD variance, which is of course the second central mode of the exit distribution, we all know. This can be also given by this equation. So this way you can calculate the value data which have been given to us. This is the way we can calculate the value of the variance. And RTD peak would occur at this one. And for times in series model, T peak is given by in particular this equation right here. Okay, these are all taken from the standard textbook. Let's take the numerical example just to show you, how to calculate, how to construct this ET curve and how to calculate the standard deviation. Let's show. So we have injected a tracer here, and these are the concentrations what we are measuring. So we are measuring the concentration here at let's say equal time intervals of 2 minutes here, and we measure the concentration of the tracer. As I said, could be conductometrically, could be a conductivity meter, or we could be like a visible spectrophotometer. So let's say the concentration of the traces measured are these values right here. So Ci delta 2 will be equal to 1 multiplied by 2. So this would be equal to again 1 multiplied by 2. So this is the total summation. And Ei is equal to Ci divided by the summation of Ci delta t. So just 1 divided by 20, 1 divided by 20. These are all going here. Okay, in the next step, I'm just showing you the curve here of the tracer concentration versus time. So these are the actual data points which have been given over there. These lines don't exist. These are just for connecting lines or visual guides only. Okay, to calculate the mean residence time, we know that this the mean residence time is given by this equation right here, which we have given right here. This is the equation for the mean residence time right here. Okay, and what we can see here. So this is Ti in delta T basically here. This is called Ti in integration Ti EIT, and this is delta T. What we have right here. EIT delta T, and we know EI is equal to CR at that particular point divided by the total summation CI delta T. So we put them right here. So this is equal to Ti, and this is equal to Ci delta T divided by, of course, summation of Ci delta T. And of course, these two delta T cancel out. So this is Ti, Cr, summation of Ti with Cr. So how do we do that? We're just going to use this equation right here. We have already calculated for each Ti what's the value of Ei, and we know delta T is equal to 2 minutes. So for each Ti, let's take this one. So for this 1 minute, we know that this Ei value is 0.05. So what we do is 1 multiply 0.05 into 2, which is delta T. Let's look at the second one. At point, this is the second point. This Ti is 3, and this of course is 0.05. So here we get 3 multiplied by 0.05 into 2, which is delta T is 2. So this way we do the calculation. As you can see, this becomes equal to 5 minutes, which is the value of T bar for our problem. It has been construed in such a way that it kind of mimics our problem. And you calculate the variance according to this equation right here. For each Ti, we have already calculated delta T. We know the value of Ei from this table here. We know the value of Ei from this table here, and we know the value of delta T is equal to 2. So we do this calculation, we get 4 minutes squared, which is the value. So we got in our problem, okay, the problem given to us. So this is basically the way, as you can see. So the point of this one is that just by injecting a tracer in your actual reactor, and measuring the concentration of the tracer, you can determine the value of the average residence time, and you can calculate the value of the variance by using this particular calculation method. That is the purpose of these two slides. Okay, what are the key points and the lessons learned from this problem solution? A true pulse input is like a Dirac delta function, infinitely narrow. We draw it as a very thin spike. For RTD, mean residence time, of course, is given by this equation we have seen, where T bar is the average time fluid elements are expected to remain in the reactor. Okay. RTD variance is given by this equation, which you have just seen in this example. We have calculated this one. A non-ideal reactor may be represented by an equivalent tanks in series model using this equation, which you have given, and we calculate the value of n is equal to 6.25 from this problem. An equivalent form of dimensionless variance, which you can see sometimes, which is given by this equation in the books. You will see this equation, but theta is a dimensionless one, which is T over tau. So basically, these two are the same. Okay, because we are using in some books you might see this one right here, whereas in our problem you might have seen in our solution use this one right here. So there's an extra tau here because just tau comes from dimensionalizing the residence time right here. So the key point is for n is equal to 1, that's for one ideal CSGA. This is complete back mixing, where n tends to infinity is an ideal plug flow reactor. If it is between 1 and infinity, there's an intermediate behavior between an ideal CSGA and an ideal plug flow reactor. For us, it's equal to 6.25. Now, once we know the value of n, we can calculate the non-ideal reactor. We can calculate the value of the conversion using this particular formula. This is for a first order reaction. Remember, this is for a first order reaction in the tank. It's tanks in series. So this way we can calculate the conversion. So by calculating the conversion in a series of n tanks in series model, we can calculate what would be the actual conversion in the actual reactor. Okay, because this value of n is obtained from the experimental data of sigma t squared on this particular non-ideal reactor. Industrial relevance of this problem: early tracer breakthrough. If there's an early tracer breakthrough, that means if there's a reactor here and you are measuring and you inject and immediately throw there is a tracer coming in. So basically that shows short circuiting, channeling, and pore inlet distribution. So if there's like this one, immediately as the fluid comes in, it immediately goes out. That's short circuiting. That's a channeling. There could be pore inlet distribution, etc. Long RTD trail, if there's a RTD trail is like just extending tail, and then there's a stagnant regions. There is a lot. So in the reactor, there might be a lot of stagnant regions, material trapped behind the coils and internals. Let's say if there is a coils and internals, etc. It might there's a problem of trapping of this the fluid of the reactants coming in. So that's another problem. Broad RTD, if it's a very broad RTD, excessive back mixing, combined bypassing, and stagnant zones. The actual answer, of course, is that the conversion is, of course, here. We have already calculated the conversion is 82.4%. So that's the answer. The answer is 82.4%.